Yeah, welcome back, dear friends. Uh, Today we'll be discussing about another module where already we have completed our water tank, and now there is another module called design of circular slabs. So this is going to be the first lecture on design of circular slabs. So this is what the syllabus under KTU and circular slabs and the stresses involved in this and the reinforcement detailing and simply supported, and three there will be three cases like simply supported, fixed and partially fixed subject to uniformly distributed load alone. Okay, this is the first part of this chapter. After that we will be going for the design and detailing of spherical and conical domes. Okay, so that's all with this module actually. Let us see the first portion. First, design of circular slabs. Yeah. So I think last time we have seen like how do we design. I mean DCS1 I am talking about. And, we have seen how do we design a rectangular slab. Yeah. So rectangular slabs, we know that it will bend orthogonally, and only bending moment and shear force is mainly involved in that. Whereas in circular slabs, usually the circular slabs, we go for circular slabs for a rooms of circular in shape or traffic islands like this, wherein junctions and all, traffic police, you know. So for regulating the traffic, they'll be having either street structure or concrete structure like this with a single column. It will be the circular slabs will be resting on it. Okay, and circular water tanks, covers, circular underground tanks, sumps we have seen the last class, last previous chapter. Okay, so these are the main applications wherein you will be looking for circular slabs actually. Okay. So let us take the case of a circular slab like this. Let us see what are the stresses mainly involved in it, or what are what type of moments, or how does it behave, how does it bend like. So as you can see here, see these blue color lines, particular. So the one such case is like the slab might bend in I mean perpendicular directions like this, okay, in a radial direction. Okay, so and this will create a moment also. So it's called the radial moment. Okay, another chance is that because of the circular in shape and this is full of water, and because of the water pressure which the wall is subjected to, because therefore there is a chance circumferential stresses will develop, which will try to crack the beam, like because these red color lines are called the cracks because of the circumferential stresses. Okay, so it will try to pull it apart also. Okay, so there are mainly two types of stresses. One is radial stresses, or radial moments, which is mainly due to the bending of the slab in orthogonal directions. Another one is circumferential stresses, like this, because of the bending on the circumferential in a tangential way, or because of the hoop stresses. Okay, so you can see here it might look over proportioned, actually out of proportion. Anyhow, still let us say this slab bends like this. So this red color lines, and similarly this red color line, it is bent in orthogonal direction. So because of the radial moment it will generate. Similarly, this you see here, so this blue color lines, this is because of the tangential or hoop stresses. So mainly you can see like radial stresses will develop because of the radial moments. So this another case is that because of the support conditions, you will be having the radial moments at support and center also. So mainly two cases, one is at the center, other one is at the support. So we need to find out the radial stresses or radial moment, normally denoted by m theta. Okay, it is at support and center. The same way as I told you, because of the hoop stresses or tangential stresses, tangential moments are developed actually, because of which this is also at support and center. Then whenever a beam bends, you know that there is one portion will be compression and another portion will be tension. So you will be having tensile stresses as well as compressive stresses. Okay, and of course there is a shear, radial shear will also come because of the tangential stresses. Okay, so these are the main things, main forces or main stresses mainly involved in this case of circular slabs. So we'll be looking into mainly tangential stresses, tangential moment and radial moment, and the shear also. Normally in the slabs, as you know, the thickness is too small, the shear will be always in safe actually. Anyhow, we'll be checking that also. So that's all with that one. So in this chapter, we will be dealing with the three cases mainly. One is, as you can see here, there will be three cases mainly. One is the support conditions, simply supported condition with the UDL, because we will have to go through only UDL only, because we don't have any other loads in your syllabus now at present. Okay, so we'll be dealing only the UDL cases, simply support the circular slab with the UDL. Other one is simply support circular slab with the fixed support. I mean, there's fixed support with the UDL, circular slab fixed ends with the UDL, and circular slab with partially fixity at the support with the UDL. So these are the cases. So let us, we don't want to go into the, the derivation of all these things. We will see, we will write down the formula for radial moment and tangential moment in support and center as well in each case. Okay. So, and before we go into that, these are the normal reinforcement arrangement. With reinforcements can be arranged in three different ways actually. The one way is just like a diagonal, orthogonally we will place this black color one like this, and horizontally like this also. This to take care of both the radial as well as tangential stresses. Then mainly because another thing is that at the support there is a chance of slip because of the circumferential stresses. So for that we need to provide the rings, okay, for a distance of 2/3 LD. Okay, so that also we need to find it out. One case is like this, 90-degree the reinforcement, and at the end for a distance of 2/3 your what do you call the rings to take care of hoop stresses. Another arrangement is like this, the hoop stress, the rings will be from the center, concentric circles, reinforcement will be provided like this, see, 1 2 3 like this, and the reinforcement it is like this. Okay, so here what is problem is that we cannot take all the bars up to here. These bars we cannot take up to here because there will be high congestion here actually. So the spacing what we got we will be providing here. As we come towards the center, we will cut the bars somewhere. Okay, to maintain the spacing or to not to have a congestion at the center. Okay, this is another case. Then and even better way is, the center will be providing a mesh like this, a rectangular mesh. The green, the blue color as you can see here, it will be like this way, and these bars, we will go inside the mesh for a distance of LD. This distance from the edge of the mesh to here is LD. Okay, then your hoop stresses, the rings will be providing like this actually. These are the main three ways we will provide. Okay, so we will discuss in detail. So let us see. Then another case like as I told you before, there will be three cases will be there. Okay, so this is the first case. It's simply supported case. The beam is simply supported. The slab is simply supported at the ends and carrying a UDL. The first figure shows your tangential circumferential moment diagram. So the center it is 3/16 WR square, and at the support it is 2/16 WR square. Okay, or otherwise I can say like support moment is 2/3 of center moment actually. Okay, the moment at support, moment at support in means m theta at support, moment at support is equal to 2/3 of m at center, especially in case of tangential stresses, tangential moment. Okay, right. and okay, moment at support is equal to 2 by third of moment at center. And the another one is this diagram shows the radial moment actually. So this is also center, it is 3 by 16 W r square. The both cases the center value is 3 by 16 W r square, whereas at the support it is 0. Okay. So for a simply supported one, so just to keep in mind these values, we are not going into detail of this how these values are getting. It is beyond the scope of our syllabus, so we don't want to go through that. And this is your shear stress, radial shear actually. This is for radial shear. Radial shear we normally denote by FR. This is radial shear. Okay, this is WR by 2 here and WR by 2 here. Okay, so these values we need to keep in mind. So another case is slab partially supported, partially fixed at end. So before that we can go through this fixed and the slab is fixed at supports and carrying a load W. Okay, UD load W. Alright. So here also we have the first case is a tangential support actually, tangential moment diagram. So this will be center, it will be W r square by 16. At the support it is 0. There will not be any radial stresses at the end. W r square by 16. And for a radial moment, I mean tangential moment. Whereas in the radial moments, the center it is W r square by 16. At the support it is 2 W r square by 16. It is negative. Okay. So because of the fixity, there will be negative moment will come, which is 2 W r square by 16, and the center it is W r square by 16. So normally this point is called a point of contraflexure. At the end you can take around 0.18 r to 0.2 r. So normally we can take 0.2 r. R is radius actually. This distance is radius. So normally we can take that value, point of contraflexure. So because of this negative moment, we need to provide reinforcement will be at the support top. Okay, so these values also keep in mind for tangential hoop stresses, tangential moment, center it is W r square by 16, whereas at support it is 0. The radial moment at center it is W r square by 16 and support it is 2 W r square by 16 negative. And coming to the partially fixed case, because it will be the average of these two. Okay. So partially fixed case, for a tangential moment, center is 2 W r square by 16 and support it is W r square by 16. And for radial moment, center it is 2 W r square by 16 W. So where W is the UD load and R is the radius actually. Okay. And these are the constants. So in short, we can write it is in a tabular form like this. The type is simply supported, fixed and partially fixed. Moment at support and middle, support and middle. The first, let us say I can write like this: m theta at support. The tangential moment at support is C1 W r square. C1 is a constant. So at support C1 is 2 by 16 W r square, and at the middle it is C1 W r square. C1 is 3 by 16. 3 by 16 W r square. Okay. Similarly, for radial moment at support it is 0, and at the middle it is C2 W r. C2 is 3 by 16 W r square. Okay, same way here at fixed it is support it is 0, and the tangential moment theta, and middle it is 1 by 16 W r square. Okay, and here partially fixity, support it is 1 by 16 W r square, and middle it is 2 by 16 W r square, whereas the radial moment or tangential moment, radial moment it is minus 2 by 16 at support for fixity. The middle it is 1 by 16. And this is, I think it is a mistake, it is minus 1 by 16 and it is like this, 2 by 16. Okay. And this one, this delta indicates the deflection. Deflection is like, 3, the C3 in WR to the power 4. So C3 is the value here. Simply support 5 by 16 W r to the power 4, and fixed case it's 1 by 64 W r to the power 4, and partially fixed it is 3 by 64 W r to the power 4. So these values you can just keep in mind. Always one thing you can notice here, it is the middle The both cases, any beam, whatever the beam you take at the sub center, your radial moment and tangential moment will be same actually. 3 by 16 WR square, here also 3 by 16. Here 1 by 16, 1 by 16, 2 by 16, 2 by 16. Okay, only the support conditions moments will change. Right? So now let us go through the design procedure actually. How do we design? Because our aim is to design a circular slab. Alright? So let us see how do we design. So for the first step, as usual, you write down all the data and understand what is the support conditions. That is important actually. Is it fixed, simply supported, or partially fixed or not? The next step being, because our aim is any design, it involves finding out the moments. Okay. Then for finding out the moments, we should know the loads and the span also. So that is what we need to find out. First, assume the thickness of the slab as L by 20 to L by 40. So in our case, it is we can take it as L by 20. As a matter of fact, we can take L by 20, where L is nothing but diameter of the slab plus wall thickness. Means we should take the center to center distance. Okay, the center of the wall. Okay, so that is L. So once that thickness of the slab is got, that is the overall thickness. The effective thickness. Okay, so approximately you can take a cover of 20 mm, 15 plus 5. So you can find out the overall thickness also. Okay, once the thickness is got, next step is finding out the loading conditions. Find out the loads actually. So you'll be having only two types of loads. One is dead load and another one is live load. Live load will be given to you in the question. Dead load is, once you got the previous cases, you will get the thickness of the slab depth, overall depth into 25. 25 is nothing but the unit weight of concrete, RCC. Once you got it, so normally we'll be designing the circular slab using, limit state method. So find out the factored load. So factored load is 1.5 into W. So these things, once you got the load, our next step will be finding out the bending moment. So load is given to you, you found out the load and you got the span also. So the next step is normally we will find out M theta and MR, means radial moment and tangential moment for the support as well as center. Okay, as per the support conditions, you decide whether it is simply supported, fixed, or partially fixed or not. Then you find out these things. Okay, so you'll be getting four values. One is M theta at support and M theta at center, MR at support and MR at center. So out of these four values, take the maximum value, and using that maximum value, find out the D required. Okay, you can use SP16 and you decide the D required. D required is equal to root of M divided by 0.138 FCK into B. This 0.138 is because I have considered M25 concrete and I have considered Fe415 steel. If you are considering Fe250 or MS steel, no, this value will different. You will get it from SP16. Table number C, I think. Okay, table C, SP16. Okay, so once this is, if it is safe, okay, if the D required is less than the D provided, then we are on the safer side. If not, we need to increase the depth. So next step is find out the area of steel required. So area of steel, as you know, we will be finding it from the SP16 as usual. For a simply supported, singly reinforced beams, that table you should take. So find out mu by bd square. So using mu by bd square and the table in SP16 for singly reinforced beams, corresponding to which SCK, you find out P, the percentage of steel required. Once you got P, using P you find out AST. As usual, we have done a number of ways. And once you got AST, find out the spacing as usual. So the next step will be you check for shear actually. So usually how do we check the shear? We will find out the actual shear stress by the formula V by BD, where V here it is WR by 2. Okay, where W is the load and R is the radius. Then once you got tau v, which is v by bd, then using table 19 of IS456 and using the percentage IST, you find out the permissible shear stress that can be taken by the concrete, tau c. If tau c is greater than tau v, we are safe. If not, increase the thickness. Okay, once we do the problem, it will be clear for you. So another thing is that once that is done, so whatever the steel what you have found out using step number 16, it is the main steel like this like this like this. So as I told you, there can be some radial stresses also at the support. So we know that moment at the radial the radial moment mr is equal to 2 by 3 of m theta. Okay, so AST hoop steel is 2 by 3 of you know the AST at support. I think is there any mistake happened? It's correct only, right? The simply support case m theta. M theta at support is 2 by 3. This is not MR. I think there was a small error. This is m theta. M theta. Okay, not MR. M theta is equal to m theta at support and 2 by 3 of m theta at center actually. M theta at center. Yeah. Therefore, AST required for hoop tension at support is 2 by 3 of AST at center. So using this one, we need to find out the number of rings. These rings should be provided for a distance of 2 by 3 LD. LD is nothing but development length. That you know it already. You already done before 5 into sigma s divided by 4 tau BD. Okay, so that when we do a problem, it will be clear. So detailing is very important actually because this is a must at the support. Okay, thank you very much. So we'll continue next class. Thank you.